Hi there. In this lesson, we're going to look at some other angle relationships when you have angles that are being formed in different locations with respect to the circle. Okay, so in your notes packet, you're going to want to find this page in your notes, section 10.5. And before we fill this out, I want to look at an animation, a little diagram that I have made up for you. So here we have an angle in which the angle formed is on the circle. So when we say on the circle, remember that means the vertex must lie on the actual circle. So we're looking at the green portion. If it were in the white, so in here, that means the angle would be inside the circle. So on the circle means it must be on the actual green ring of the circle. Okay, so we already have a name for this type of angle. This is an inscribed angle, and we already know that the relationship is that the inscribed angle is equal to half of the intercepted arc. Okay, so here we see that we have the measure of arc BC is 99 degrees, and the measure of angle CDB is 49 degrees. And as we change that arc, we can see that if you kind of look at the measurements there, we can see that those measurements still stay true to that rule. So half of the intercepted arc is what we get for our angle measure. And it doesn't matter where we have this angle that's on the circle. If it's intercepting that arc, that's what the degree measure is every single time. So depending on how your picture looks, it could look like something like this maybe. And these don't have to be segments either. These could be lines. So this could be a line that extends up through here, another line that extends out past the circle. But the key idea is that this vertex is on the circle, so that means that the measure of this angle is going to always equal half of that intercepted arc. Okay. Next one we want to look at is when we have an angle intercepting outside the circle, or the vertex of our angle, sorry, is outside the circle. So here we have angle E. It lies outside our circle. We have this intercepted arc, arc BC, and its measure is 99 degrees. And then we have this intercepted arc, GH. GH is equal to 54 degrees. And then over here, it tells us that our angle E is equal to 23 degrees. So what we're looking for is a relationship between 99, 54, and 23. Okay, so there must be some sort of relationship. Okay, well, if we kind of look at the numbers, and maybe if we drag this vertex around a little bit, we can see how those numbers change. Notice arc BC, that's not changing at all. But the smaller arc GH, that's getting a little bit smaller as I move my angle closer, which makes my angle get bigger. And then as I move out, arc GH, the second intercepted arc, is getting bigger, while the angle E, is getting smaller. So, and somehow it must be all related back to the measure of arc BC, because we know there's got to be a relationship there. All right, so we could try a couple of things. Let's see, I'm looking for a calculator here. Here's a calculator. All right, so let's say we wanted to just look at the relationship between BC, and let's see what happens if we divide that by 2. Okay, well, that gives us 49.33, not the angle measure that we're looking for. Okay, so let's see what happens if maybe we somehow combine that with the measure of arc GH. So let's add the measure of arc GH. Okay, that's 133.5. And let's see what happens if we take that and divide it by 2. So it's okay. And we want to take this. Let's see, somehow I'd like to divide that by 2. Put some parentheses around that. Now we're going to say divide that by 2. 66.75. Still not quite right. In fact, that looks like it's almost twice this. I wonder what would happen if maybe instead of adding these two arcs together, maybe we need to subtract them. We've had some problems like that where we've had to subtract arcs. So here I have the measure of arc BC, which was our 99 degree arc. minus GH, our 35-degree arc. When we divide that by 2, we get 31.9082. Wow, if we round that up to the nearest whole number, that gives us 32 degrees. Let's see if that's always true. Let's move our angle E out further away, 19.87 compared to 20. We'll move it in a little closer, get it almost touching the circle. 46.8, 47, looks good. Let's see what happens if we change these arcs. So if I drag and make the circle bigger and make the arc bigger, still the same relationship holds true. 134 minus 67 divided by 2 gives us this one, or gives us 33.62, which is still 34 degrees. Let's see if maybe we can change this. Try to change this arc GH a little bit, and it's not going to let me change that. Okay, let's maybe make this a little even tinier yet. We didn't see small. Okay, so 29 degrees, 21 degrees, take their difference, divide by 2, 3.67, compared to the angle outside, 4. So I think it's probably a pretty safe conjecture to say that if we take the difference in the two intercepted arcs, so intercepted arc BC, intercepted arc GH, those two arcs that are being intercepted, if we subtract them and divide by 2, that gives us the angle that's formed outside the circle. Okay. Now we have a final relationship when we have an angle where the vertex is inside the circle, but notice my picture, inside the circle, but it's not at the center, right? Because we already know that if we have an angle in which the vertex is the center of the circle, that's just a central angle, which equals the measure of the intercepted arc. Here we have an angle, we have vertex K, so if we're looking at angle CKB, we see that measure is 94 degrees, and it's inside the circle, but it's not the center. All right, so if we're looking at its intercepted arcs, we've got this arc here, BC, that goes with that angle K. Or if we look at the other side of angle K, which we know this blue angle, JKI, compared to the green angle, CKB, we know those two angles have to be exactly equal, right? Because those are vertical angles. But if we look at angle JKI, look at its intercepted arc, it's 90 degrees, not 99. So there must be some relationship between these two intercepted arcs and our angle K. And it doesn't matter if we're looking at green angle K or blue angle K, they're going to be exactly the same measure because they're vertical angles. So if we look at 90 degrees and 99 degrees, we have 94, which is our answer. Looks like 94 is somewhere in between 99 and 90. So let's do a calculation here and check and see what happens if maybe we average those, right? Because 94, that seems to be pretty much right in the middle of 90 and 99. So let's try that out. We have the measure of arc JI, the first intercepted arc, plus the measure of arc BC, our second intercepted arc. We want to try to take an average, so let's throw some parentheses around that. So we're going to add those together, and then we want to divide that answer by 2. So we have the sum of the intercepted arcs divided by 2. That's an average. And what do you know? 94.44 degrees, which if we round to the nearest whole number, that gives us exactly what we had for our angle measure. So let's see if this always works. Let's see what happens if we drag these angles around. So here we have everything's changing. We have angle K, which is now 55 degrees. Our two arcs are 19 and 90. And look, the average of those two arcs is still the same thing as what our angle K was. So let's drag it the other way, make it a little bit bigger on the other side. So 124 and 90 degrees are our intercepted arcs, and the angles are still holding to that relationship. If we take the average of the arcs, that is what the measure of our angle is. Okay, remember if we take that, let's see if we can, it's not going to let me do that. I was going to say we could drag that and make that the central angle, but it's not going to let me, I didn't construct it to let me do that. Okay, so it looks like we can probably fill out those relationships back on our note sheet then. So let's look at this page. What is the relationship between an angle on the circle and the intercepted arc? Well, we just said that's the same thing as an inscribed angle. So same, oops. as an inscribed angle. Measure of the angle is half the intercepted arc. So let's change that color to purple. Let's make it a little bit bigger for you. There we go. So same as an inscribed angle, the measure of the angle is half the intercepted arc. Okay. If we come down to our second picture, here we have an angle inside the circle. What's the relationship between an angle inside the circle and the intercepted arcs? Well, we just said that the measure of the angle is the average of the two intercepted arcs. And we'll underline that. And let's see if maybe we can go back and get, I'm going to copy that. And then our third one, what is the relationship between an angle outside the circle and the intercepted arcs? For that one, let's go back to that picture. That was the one where we were able to subtract the arcs and then divide by 2. The measure of the angle is half the difference of the intercepted arcs. All right, so there we have it. We've got 3 different relationships regarding angles and arcs. If you have an angle in which the vertex is on the circle, it's going to equal half the intercepted arc. If the angle is inside the circle, we're going to add the arcs and divide by 2, or take an average. And if our angle is outside the circle, we're going to take a difference in the 2 arcs and then divide by 2. Okay, so you'll want to bring these completed with you to class, and then we'll do some example and some practice problems together in class tomorrow. We'll see you then.